Hello, hope you are doing well. Welcome to another video on Circuits Decoded. First of all, I'd like to apologize for being late. It has been a busy few weeks. Um, Today I want to talk about a few analog circuits with positive feedback and discuss their stability. So as analog engineers, we are often alarmed at the sound of positive feedback as it relates to instability. But at the same time, we are comfortable with circuits like oscillators and latches that work on the principle of positive feedback. Likewise, there are several circuits in the analog domain which also have positive feedback in them, but we don't quite notice the positive feedback at the first glance. One such circuit is the supply-independent bias generator, as shown in this diagram. The reason it's called supply-independent biasing is because if we work out the DC current expression of the branch currents I out, we can see that it's independent of VDD, and it depends on the device properties, the source resistance Rs, and the factor K. The factor K is the ratio of the W over L of the NMOS transistors M2 and M1. Interestingly, if we work out the transconductance expression for the transistor M1, we can see that it's not only independent of VD, but also independent of the device properties. And it only depends on the source resistance Rs and the factor K. So if we keep Rs fixed through some techniques such as trimming, we can essentially make GM constant. Hence, this circuit is also referred to as constant GM biasing. An interesting application of this is to realize a PVT insensitive amplifier as shown here. If we use the gate bias voltage of M1 to bias the tail current source of a diff pair, we can realize a PVT insensitive gain. However, the assumption here is that the NMOS transistors used in the differential amplifier must be of the same type as M1 and M2 and use the same channel length. So now let's see the gain of this diff pair, which is GM times RD, and GM is the same as this expression. Then we can simplify it as shown here, which shows that the gain is essentially a ratio of two resistors, RD and RS, and some constant factor. So it is PVT insensitive, at least to a first order. This is a nice little trick to make an open loop amplifier with stable gain. However, the reason I'm talking about this circuit is not because of its biasing properties, but because of its feedback loop properties, which is from M2 to M1 through this current mirror. The question is whether this loop is positive or negative feedback. So we can quickly check this. If we increase the gate voltage of M2, the current through the current mirror increases, which increases the gate voltage of M1. So we can see that the return voltage and the test voltage are in phase. So this is indeed a positive feedback. Okay, we know that the type of feedback here is a positive feedback. But does it mean it's unstable? Let's find out. Recall that for a negative feedback loop to be stable, when the phase drops to 180 degree, the loop gain must be less than 1. Or in other words, for any positive feedback loop to be stable, the loop gain has to be less than 1 at all frequencies. To find out the loop gain for this circuit, we apply a test voltage at the gate of M2 and find out the return voltage VR, which is shown here. The small signal current I is simply given by the effective transconductance GM2 over 1 plus GM2 RS times VT. The return voltage VR is simply the mirrored current I times 1 over GM1. Then the loop gain L is simply VR over VT, which is given by this expression. Now for all practical values of GM and RS, it can be shown that the loop gain is indeed smaller than 1. And hence, for all frequencies, the loop gain stays below 1 and hence is stable. An interesting interview question is, what happens if we swap the diode connections of the current mirror as shown here? Will the circuit still work? To answer this, we need to again find the loop gain. To do this, we break the loop at a convenient spot as shown here and apply a test voltage source VT at the gate of M1. Now we need to find the small signal current I and the return voltage VR, which are shown here. The small signal current I is simply GM1 times VT, and VR is simply I times the impedance at node VR, which is 1 over GM2 plus RS. The loop gain then is simply VR over VT, which is shown in this expression. Now for all practical values of GM and RS, it can be shown that the loop gain L is greater than 1. So this loop is unstable, because when the loop gain is greater than 1, the phase drop is less than 180 degree. So this setup cannot be used. Now, can you think of any positive feedback circuit that has loop gain greater than 1 but still works? Does such a circuit even exist? Indeed, there are cases when the loop gain is greater than 1 and yet the circuit is stable. One such example is the IPTET current generator as shown in this diagram. Let me first go through the circuit operation first, and then we can analyze the loop. Assuming that the circuit is stable, the op-amp with a very high gain of A will force the node voltages Vx and Vy to be equal. And the upper PMOS transistors will ensure that the branch currents are equal as well. So the current through the resistor R1 is proportional to the difference of the VBE of the bottom BJT transistors Q1 and Q2. Also, since the currents of these transistors are equal, their GMs are also equal and is shown here. Now we can see that there are two loops, L1 and L2. However, we do not know which of these loops is negative feedback and which one is positive feedback. To know this, we need to find the loop gain of each of these loops. However, we do not know at this point the polarity of the input terminals of the op-amp. So let's find out the loop gains without this knowledge. The loop gain of L1 is simply minus A times GMP over GMQ1. The minus sign is because of the voltage current relationship of the PMOS transistors. Similarly, the loop gain of L2 is given by this expression. Now the question is, which loop should be positive and which loop should be negative feedback? If your answer is L2, you are correct. The idea is to make the loop gain of the negative feedback loop to be greater than the positive feedback loop so that the overall feedback is negative. And hence, the input terminal polarity should be like this. So I hope this video was informative. I'll be back with more videos. Stay tuned and please subscribe to my channel, and I'll see you next time.